This is SpaceTime, Series 20, Episode 51. Coming up on SpaceTime, it's time to celebrate Asteroid Day, so we'll check out the major likely fatal effects of an asteroid impact on Earth, NASA's mission to the metallic asteroid world of Psyche, and Albert Einstein right again. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
June 30th is Asteroid Day, marking the anniversary of the largest asteroid impact in Earth's recorded history, the 1908 Tunguska event. It was on this day at 17 minutes past 7 in the morning local time that an asteroid airburst about 10 kilometres above the Tunguska River region of Siberia in eastern Russia. The blast devastated some 2,150 square kilometres of forest, leaving some 80 million trees flattened and reduced to matchwood. The blast probably released as much energy as a 5-megaton thermonuclear device. The shockwave from the explosion was detected by seismic stations across Europe and Asia, and was the equivalent of a magnitude 5 earthquake. Light from the impact lit up the night skies in London a third of the way around the globe, making it bright enough for people to read newspapers at night without the need for lighting. In fact, over the next few days, the night skies across Europe and Asia remained aglow. It's been hypothesized that this was due to light passing through high-altitude ice particles that had formed in extremely low temperatures. It also produced fluctuations in atmospheric pressure strong enough to be detected across Britain. Dust from the event affected atmospheric transparency for several months, limiting astronomical observations around the world, including the Mount Wilson Observatory and the Smithsonian. Although Tunguska is classified as an impact event, no actual physical impact crater has ever been found. Studies have yielded different estimates for the meteoroid's size, on the order of 60 to 190 metres, depending on whether the body was actually an asteroid or a comet. Since 1908, there have been literally thousands of scientific papers published on the event. Back in 2013 on SpaceTime's predecessor Star Stuff, I reported on new scientific analyses of samples from a peat bog near the centre of the affected area, which examined fragments that appear to be of meteoritic origin. The epicentre of the Tunguska event was so remote that it wasn't until 1921, almost 10 years after the impact, that a scientific expedition finally reached the site. People in the hills northwest of Lake Baikal told researchers they saw a column of bluish light, nearly as bright as the sun, moving across the sky. And about 10 minutes later they saw a flash and heard a sound similar to artillery fire. Eyewitnesses closer to ground zero saw the source of the sound moving from east towards north. The sound was accompanied by a shockwave, powerful enough to knock people off their feet and smash windows hundreds of kilometres away. Now, if all that sounds just a wee bit familiar, it's because it is. Back on February the 15th, 2013, another meteor, somewhat smaller, airburst in the skies above Chelyabinsk in the Russian Urals. Recorded on dashcams and security cameras across the city, the meteor streaked across the early morning sky, followed minutes later by a powerful blast wave, shattering windows, damaging buildings, knocking people to the ground, and causing more than 1,200 injuries. The majority of those injuries were caused by broken glass, sent flying into the faces of unknowing locals peering through the windows after the meteor's bright flash. But there are also victims who suffered more serious burns and even temporary blindness from being too close to the impact site. Scientists estimate the Chelyabinsk meteor was between 17 and 20 metres wide, with an estimated mass of about 11,000 tonnes. Asteroid Day was sanctioned by the United Nations in 2016. It's designed to be a global day of education, to raise awareness about the dangers posed by asteroids, and the need to use science and technology to increase our knowledge and understanding about these harbingers of doom, protecting humanity and the planet from future impact. And remember our Star Stuff and our SpaceTime motto, asteroids are simply nature's way of asking, how's that space program coming along? This is SpaceTime. I'm Stuart Gary. Based on a statistical analysis, you're more likely to be killed by an asteroid impact than you are in a plane crash. That's because while plane crashes are far more frequent, the death toll from a major asteroid impact would be staggeringly higher, likely in the order of tens of millions of fatalities. Of course, in reality, the likelihood of an asteroid impact is low. Mind you, just about every astronomer on the planet agrees the Earth will be hit by another major asteroid event, but it probably won't be happening tomorrow. Earth is struck by an asteroid, say 60 metres wide, approximately once every 1,500 years. And an asteroid 400 metres wide is likely to strike the planet every 100,000 years. The last really big one was the KT boundary event asteroid, a 10 to 15 kilometre wide space rock which slammed into Mexico's Yucatan Peninsula 66 million years ago, causing a major mass extinction event which killed 75% of all life on Earth, including all the dinosaurs other than birds. Something this size hits the Earth roughly every 60 million years. So, based on those calculations, we're already overdue for the next one. Now, a new report in the journal Geophysical Research Letters has concluded that when a big asteroid does hit the Earth, violent winds and shock waves are likely to cause the greatest number of fatalities. The study was exploring 7 key effects associated with asteroid impacts: heat, pressure shock waves, flying debris, tsunamis, wind blasts, earthquakes and seismic shaking, and impact cratering. The study then estimated the likely lethality of different sized asteroid impacts. Finally, the researchers then ranked the effects from most to least deadly. In other words, how many lives would be lost to each effect. Overall, wind blasts and shock waves were likely to claim the most casualties according to the study. The experimental scenarios found that these two effects accounted for more than 60% of all lives lost. The shock waves arise from a spike in atmospheric pressure, and they're capable of rupturing internal organs, while the wind blasts carry enough power to hurl human bodies and flatten forests. The study's lead author, Clemens Rumpf from the University of Southampton, says it's the first study to look at all 7 impact effects generated by hazardous asteroids and estimate which, in terms of human loss, are most severe. The findings could help hazard mitigation teams better prepare for asteroid threats. That's because it details which impact effects are most dominant and which are less severe, and therefore where resources should best be allocated. Rumpf and colleagues used models to pepper the globe with some 50,000 artificial asteroid impacts, using asteroids ranging from 15 to 400 metres across. And that just happens to be the diameter range of asteroids that most frequently strike the Earth. The researchers then estimated how many lives would be lost for each of the 7 effects. Interestingly, they found land-based impacts were on average an order of magnitude more dangerous than asteroids that landed in the oceans. You see, while large ocean-impacting asteroids generate enough power to trigger massive tsunamis, the wave energy would likely dissipate as it travelled and eventually break when it met the continental shelf. The authors claim that even if a tsunami were to reach coastal communities, far fewer people would die than if the same asteroid struck land. Overall, they found tsunamis would account for 20% of all lives lost. The study found that the heat generated by an asteroid impact accounted for nearly 30% of all fatalities. But given enough warning time, affected populations could mitigate harm by hiding underground. Seismic shaking, in other words earthquakes, was of least concern, accounting for only 0.17% of casualties. Cratering and airborne debris were also less concerning, both generating fewer than 1% of deaths. The study also concluded that only asteroids greater than 18 metres in diameter would be lethal. Many of the asteroids at the lower end of the spectrum disintegrate in Earth's atmosphere. In other words, they airburst before reaching the planet's surface. But they do strike far more frequently than larger asteroids, and they generate enough heat and explosive energy to cause a great deal of damage, as evidenced by Tunguska and Chelyabinsk. Rumpf says the study's findings could help mitigate loss of human life. Small towns facing the impact of an asteroid, say 30 metres across, would probably fare best by being evacuated. However, an asteroid 200 metres wide heading for a densely populated city poses a far greater risk and therefore warrants a far more involved response, such as mounting a deflection mission to push an asteroid out of the way. Of course, all that depends on warning time. The greater the warning time, the better you'll be at preparing for its arrival. Knowing decades to centuries in advance gives you the best chance of survival. The problem with all that, of course, is that right now the United States is the only nation on Earth undertaking any sort of a significant asteroid warning project. And that's focusing primarily on the Northern Hemisphere. After all, that's where America is. Despite concerns from astronomers worldwide, no similar program is being undertaken south of the equator, since one of the planet's best-known asteroid hunters, Rob McNaught, lost his funding in 2013. McNaught, once described as the world's greatest comet hunter, was using a small telescope at the Australian National University Siding Spring Observatory to search the southern skies for potentially Earth-impacting asteroids. And he was highly successful at that job, discovering no less than 82 comets and a staggering 483 asteroids and minor planetary bodies. Sadly, all that stopped when the money ran out. And while greedy politicians on both sides of the political fence can find millions of taxpayer dollars for election pork barrelling, overseas study tours, VIP jet travel for their families, hefty self-indulgent pay rises and other goodies to keep their snouts in the trough, they just couldn't seem to find the paltry $100,000 needed to keep the only search for Earth-impacting asteroids in the Southern Hemisphere operational. Shame on all of them. I'm Stuart Gary. This is SpaceTime. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, and on Facebook just go to www.facebook.com/SpaceTime with Stuart Gary. And sticking with the asteroid theme in today's show, NASA's Discovery mission to a unique metallic asteroid has now been moved up by a year, with a launch date now slated for the middle of 2022. The earlier launch date will mean a more efficient trajectory, bringing the planned arrival time forward to 2026, 4 years earlier than the original timeline. The target is 16 Psyche, a 200-kilometre wide space rock located in the main asteroid belt between Mars and Jupiter. 16 Psyche is classified as a Type M metallic asteroid, primarily a solid lump of iron and nickel. In fact, it's both the largest known metallic asteroid and also one of the 10 largest asteroids in the main asteroid belt. Psyche seems to have a surface that's about 90% metallic iron, with small amounts of pyroxene. The iron reserve on this asteroid is said to be worth about $10 quintillion, which is exponentially higher than the combined GDP of every country on Earth, which back in 2015 totaled about $74 trillion. Last year, NASA's Infrared Telescope facility on Mauna Kea in Hawaii found traces of water on the asteroid, probably hydroxyl ions. The traces are likely to be the result of past impacts, with smaller asteroids containing volatile substances such as carbon, hydrogen and water. The Psyche mission will help scientists better understand the building blocks of planetary formation by allowing them to study a previously unexplored type of world. Astronomers want to determine if 16 Psyche is an exposed protoplanetary core, or if it's some unmelted primordial material. Researchers also want to map its surface topography and find the relative ages of different regions on the asteroid's surface. The mission will perform science observations from 4 staging orbits, with the closest orbit being just 45 to 120 kilometres above the asteroid's surface. The spacecraft's science payload includes multispectral images, a gamma-ray and neutron spectrometer, magnetometers, and an X-band radio telecommunications system. The spacecraft's new flight path eliminates the need for an Earth gravity assist, which ultimately shortens the cruise time, and also allows the probe to stay further away from the Sun, thereby reducing the amount of heat protection needed for its delicate instruments. All this allows the mission to get to the asteroid twice as quickly and far more cost-effectively. The trajectory will include a Mars gravity assist in 2023. 16 Psyche is an amazing metallic world. It offers scientists a unique look at the violent collisions which created the Earth and other terrestrial planets. The Psyche spacecraft is being built by Space Systems Loral in Palo Alto, California. The Psyche mission will be led by Arizona State University, with NASA's Jet Propulsion Laboratory in Pasadena, California, responsible for mission management, operations and navigation. This is Space Time. I'm Stuart Gary. A little more than 100 years after Professor Albert Einstein developed his famous theory of general relativity, researchers have finally been able to use its laws to directly determine the mass of a white dwarf star simply by the gravitational bending of light. In a 1936 paper in Science, Einstein lamented that there was no hope of directly ever determining the mass of a white dwarf by this method, even though theoretically it should be possible. However, thanks to developments in technology unforeseen in Einstein's time, scientists have now finally been able to use the bending of distant starlight by gravity to directly determine the mass of a white dwarf star. The results demonstrate a way for determining the masses of objects that scientists can't easily measure by other means. One of the key predictions of general relativity set forth by Dr. Einstein was that the curvature of space-time near a massive body, such as a star, causes photons passing near that massive object to be deflected by twice the amount that would be expected based on classical laws of gravity. You see, when a star in the foreground passes exactly between us and a background star, Einstein predicted a phenomenon known as gravitational microlensing, which results in a perfectly circular ring of light, a so-called Einstein Ring. The first evidence of the bending of light by mass came in 1919 when astronomer Paul Eddington and colleagues travelled to Kenya to view a total eclipse of the sun. The overcast skies cleared just long enough for a handful of images to be taken. These images of the positions of stars near the sun during the eclipse were then compared to positions of the same stars at night when the sun was far away. And just as predicted by Einstein's general theory of relativity, the positions of the stars had changed due to the bending of light by the sun's mass. And they appeared to have moved by the exact amount predicted by Einstein's equations, one of the first convincing proofs of Einstein's theory of general relativity. Yet, despite 100 years of technological advances, observing a slightly different scenario, two stars just out of alignment resulting in an asymmetrical Einstein ring, had not been achieved for stars outside our solar system. Einstein said such an asymmetry would be notable because it would cause the background star to appear off-centre in such a way that it could be used to directly determine the mass of the foreground star. Now, a report in the journal Science claims astronomers have finally been able to take advantage of modern 21st century technology to undertake just such a measurement. The authors used the superior angular resolution of NASA's Hubble Space Telescope and proactively searched more than 5,000 stars looking for just such an asymmetric alignment. Eventually, in March 2014, they found the white dwarf star Stein 2051b was set in just such a position. The research team then directed the Hubble Space Telescope to observe the phenomenon, measuring tiny shifts of just 2 milliarc seconds in the apparent position of a background star behind it. Based on this data, the authors were able to estimate that the white dwarf's mass was roughly 68% the mass of our Sun. These observations could also yield insights into theories of white dwarf structure and composition, thereby allowing scientists to independently verify the theory of how a white dwarf's radius is determined by its mass. One of the study's authors, Professor Howard Bond from Penn State and NASA's Space Telescope Science Institute, describes the measurements as a triumph not just for the Hubble Space Telescope, but also as a wonderful confirmation of theoretical predictions and a beautiful reprise of Einstein's solar eclipse observations of a century ago. The measurement of Stein 2051b's mass also holds important implications for understanding the evolution of white dwarf stars. White dwarfs are the stellar corpses of dead sun-like stars. Having used up all their core hydrogen fuel fusing into helium, they expand into bloated red giants, eventually puffing off their outer gaseous layers as spectacular planetary nebulae. All that's left behind of the original star is its white-hot carbon-oxygen core, a white dwarf, which will slowly cool over the eons of time. Understanding white dwarf evolution is important because the majority of stars in our galaxy, including the Sun, will either eventually become white dwarfs or have already evolved into them. The authors now plan to use Hubble to conduct a similar microlensing study of Proxima Centauri, the nearest star to our solar system. To find out more, Andrew Dunkley speaking with Dr. Fred Watson from the Australian Astronomical Observatory.
This is just an additional confirmation of his general theory of relativity.
Mm.
Before you zone out...
Well, you know what? You've found a way to shut me up. There you are.
Well, that's good.
Don't tell my
Let me
wife.
mention that relativity is one of the two big theories of the way we think the universe works. One is quantum theory, the other is relativity. Relativity works on the very large scales. Quantum theory works on the very small scales. Sadly, the two are actually incompatible, but never mind. That's all right. That's a problem that, again, we need to resolve. Why is relativity in the news? Well, because we in the world of astronomy, I guess, hold the general theory of relativity as our kind of fundamental guide. It's how we explain the phenomena that we see in the universe. And it's actually been proved to be correct many, many times with a very, very high degree of accuracy. So general relativity is something that is a kind of rock foundation that we build all our theories on, like the Big Bang and all the rest of it. Mm-hmm. The reason why it's newsworthy at the moment is that yet another proof of relativity has been demonstrated using the Hubble telescope. One of the things about relativity is that it predicts, it shows that if you've got mass in space, matter in space, like a planet or a galaxy or whatever, it will bend the space around it. And actually, that's how relativity was first proved back in 1919 by looking at the effect on stars of the sun's presence in the sky. It was done during a solar eclipse, actually, so that you could still see the stars even though the sun was in the same direction. And sure enough, these stars appeared to be in a different position from where they are when the sun wasn't there at a different time of the year. An interesting story that we haven't really time to dwell on, but this has been done again, but this time not with the sun, but with another star. In fact, a white dwarf star. White dwarf stars are kind of things about the size of the Earth, but with the mass of a whole star in them. So they're intense gravitational sources. And this particular white dwarf star, which rejoices in the name Stein 2051b, great name for a white dwarf, what it's done is it's passed in front of a much more distant star. And the Hubble has been able to observe this really rather remarkably, that the motion of this white dwarf in front of the other star. And sure enough, when the white dwarf passed in front of the other star, the background star's light was deflected exactly in the way that Einstein predicted. So it's the same thing as was done in 1919 with the sun, but this time doing it with a white dwarf star. It's the first time it's been demonstrated with a star like this. Einstein thought this would be impossible. He thought you'd never get a close enough alignment between two stars to witness this. But he didn't know about the Hubble telescope.
No, he didn't.
And he didn't know about the stuff that we can do these days. So it's a really nice demonstration. Once again, that Einstein was probably one of the smartest blokes in the 20th century.
Yeah, they've just released a mini-series about him, which
Indeed,
I have recorded, but I have not yet had a chance to watch, catching up on all my favourite TV shows, but I'm really keen to watch this and see how they portray him and how his life developed, because it starts in his early childhood, and it was during a pretty volatile time in the history of Germany, and growing up in a not so nice environment, from what I understand.
Well, that's right. Look, it's a fascinating story, and of course, Einstein, being Jewish, he basically became the anathema for the Nazis. They thought his theory was a Jewish conspiracy. Terrible stuff.
Oh,
what a
horrible.
terrible environment to live in.
But the good news for us is he ended up in the United States, and he did warn the Americans of the potential for an atom bomb, and they ignored him, but they eventually figured it out. And
he did some good stuff.
Yeah, incredible man.
He wasn't particularly good at relationships, and I think that's something that dogs a few scientists.
Yeah, well, it goes with the territory, I think. You've got such an expansive brain, and there's so much going on, and day-to-day stuff must seem so trivial and non-important sometimes, I guess. It's just a theory. But
you should publish that.
I'm sure it's been done.
That's Dr. Fred Watson from the Australian Astronomical Observatory speaking with Andrew Dunkley on our sister program Space Nuts. And you're listening to Space Time. I'm Stuart Gary. A Japanese H-2A rocket has blasted into orbit, carrying with it a new Quasi-Zenith Satellite Navigation System spacecraft. The Quasi-Zenith Satellite Navigation System, which will be operational next year, is designed to supplement America's GPS system and includes 3 satellites on inclined geosynchronous orbits and 1 in a geostationary orbit. Liftoff for the Michio Bikai 2 satellite occurred under cloudy skies at the Tanegashima Space Center south of Tokyo. The Mitsubishi-built H-2A launch vehicle's first stage, igniting both its cryogenic LE-7A engine, burning liquid oxygen and liquid hydrogen, and its twin SRB-A3 strap-on solid rocket boosters. The strap-on boosters burnt for 98 seconds before being jettisoned at an altitude of 54 kilometres. The first stage burns for a total of 6 minutes and 38 seconds until main engine cutoff or MECO, followed by stage separation and second stage ignition. The second or upper stage uses a single LE-5B cryogenic engine also burning liquid hydrogen and liquid oxygen. It undertakes 2 separate engine burns, between which is a long coasting phase, enough to place the satellite payload into its geosynchronous transfer orbit 28 minutes and 24 seconds after launch. Built by Mitsubishi, the 4,000 kilogram 6.2 metre long Michai Bikai 2 satellite is based on a DS-2000 satellite bus and is equipped with a space environmental data acquisition package including a particle detector and a magnetometer. The spacecraft carries enough fuel for a design life of 15 years. The mission was the 4th launch this year for the Japanese Aerospace Exploration Agency JAXA and the 3rd this year using the H-2A launch vehicle. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, your favourite podcast download provider, or direct from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more space time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts or Audio Boom. This has been another quality podcast production from Bytes.com.